Okay, so let's start. So I think so. What about the first exercise? Do you know the definition of a radical ideal? I mean, I. Okay, first let let R be a commutative ring. I subset of R be an ideal. Okay. We define root I or rad I. This is called radical of I. It is defined to be mm, all those x belongs to R such that x to the power n belongs to I
Sir,
for, oh, I haven't shared na. X to the power n belongs to I for some n belongs to natural number. Okay. 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 Now an ideal I is called a radical ideal if I is equal to root I. Okay. One immediate observation is that any prime ideal is a radical ideal. Okay. So now, so clearly, set of all nilpotents, set of all nilpotent elements. This is denoted by what? Root 0, right? Because, I mean, what is root 0? According to this definition, what is root 0? All those x belongs to R such that x to the power n is 0 for some n, right? So this is called the nil radical of R or nil R. So sometimes they denote it by this, sometimes they denote it by this. Okay. So for first exercise, so let x belongs to root 0. Okay. This means x to the power n is equal to 0 for some n belongs to natural number. Take R belongs to R. Now see, Rx whole to the power n is r to the power n into x to the power n, because because the ring is commutative, so this is 0, which implies Rx belongs to root 0. Okay, let x, y belongs to root 0. This implies there exists m n belongs to natural numbers such that x to the power m equals to y to the power n equals to 0. Okay, now take x plus y whole to the power n plus n. Okay. Break this into binomial expansion. What do you get? M plus nc. Okay, summation I running from 0 to m plus n, m plus n c. So in this expansion, either the power of x is greater than m, or the power of y is greater than n, which implies each term is 0. So this is 0. Okay, this implies x plus y belongs to this. Thus this is an ideal. So what about this? What about this? How to do this? See, you can check it element wise. Okay, you can check it element wise, like you can check it like this. So one method is that, so method 1 is like this. Method 1 is like this. You take, you take x, y belongs to this, and then show that x plus y belongs to, show x plus y and rx belongs to this for all r belongs to r. This is one method. Okay, this is one method. You can of course do that way, but we are going to use problem 1. Okay, take the ring S equals to R mod I. Okay, notice that এখন তো ক্লাস চলছে, কোথায়? ও আচ্ছা আচ্ছা, কতক্ষণ দেরি লাগবে? খুবই দুঃখজনক ঘটনা। যাই হোক, শোন না, তুই কতক্ষণ ফ্রি থাকবি? কালকে সকালে একটা আমাকে হোয়াটসঅ্যাপ করিস, তোকে ফোন করবো, ঠিক আছে? আমি এটা সত্যি জানতাম না এই কেসটা। টিচার এরকম করেছে বলতে, টিচার অর্ধেক জিনিস পড়ায়নি এটা বলছিল বোধহয়, না আজকে? হ্যাঁ হ্যাঁ হ্যাঁ, এটা বোধহয় বলছিল। মাথা থেকে সব বেরিয়ে যাচ্ছে, পড়ে সত্যি। হুম হুম, ঠিক আছে, হ্যাঁ হ্যাঁ। which implies which implies which implies root 0 in S is basically root over I quotient I in R mod I equals to S. So it is enough to show that root over 0 is an ideal in R mod I equals to S. But S is a since S is a commutative ring with unity, com ring, not unity, we use 1 to conclude the result. Okay, clear now? So basically we are going to R mod I. The 0 in R mod I is I. So the nil radical is basically root I, and we have shown it for the previous problem. Okay. Ring left ideal and right now. Don't need to do it. Prove that I is an ideal. R is to I is okay. This is a homework. Okay, these are doable. Okay, what about this? What about this? What about 5? Okay. So number 5. Uma. So they try to show that this is an ideal. Okay, I mean, let's prove this. Let Ji belongs to R. I mean, be two ideals in R. Okay, these are two ideals in R. Okay. Okay, so my claim is this is an ideal. An ideal. Okay. So like you take first you take x belongs to, oh I mean what is imology first, let me define it. Okay, all those r belongs to r such that Ri is a subset of J. Okay, that is Rx belongs to I for all x belongs to J. Okay, so take R and S belongs to sorry, take yeah, take R belongs to J is to I. So then we have Rx, Sx belongs to I for all x belongs to J. This implies since I is an ideal, R plus S times x, which is Rx plus Sx, this also belongs to I for all x belongs to J. Okay, so this implies belongs to, and yeah, let x belongs to, or maybe some other notation, say let A belongs to R and R belongs to J is to I. Okay, so we have Rx belongs to I for all x belongs to J, right? Now what is ARX? This is nothing but AX into R, since this is commutative. So this belongs to I as AX belongs to J, since J is an ideal as well. So AR belongs to J is to I. Okay, so J is to I is an ideal. Now just put J equals to R. Okay, to get this result. Okay, so see, I will give you a hint for C. Okay, I mean this is a homework, but I am telling you the hint. These are only diagonal matrices. Okay, so center of S will be diagonal matrices. Not I mean diagonal matrices means scalar multiply. Okay, scalar multiply of the identity. So this is AI. Okay. Now you can show that, take a non-singular. Take a matrix which is non-diagonal, and you will see that the product with this, AI into some other matrix, say M. This is not diagonal. Okay. Thus, this is not an ideal. What is the center of the, show that the n cross n matrix is a division ring. Division ring means a ring in which every element has a unit. The ring need not be commutative, because if a commutative division ring is a field, so that's obvious na. That is obvious, because 1 by AI is the identity. A ring with identity is a division ring if and only if no proper ideals. If S is a ring possibly without identity with no proper left, then okay, we will do another version of 7, because okay, for our discussion we will take the ring to be commutative, because otherwise there is no point in discussing non-commutative rings. The only example you should be studying is this ring, I mean the matrix ring. So do you know the definition of a field? All of you are familiar with the definition of a field, na? So let's do a lemma, or maybe first define. A ring is simple if it has only 0 and itself as ideals. Okay, so it doesn't have any proper ideal. Okay, now my claim is lemma: a ring R, I mean commutative ring, commutative with unity, is simple if and only if R is a field. So I will give you 2 to 3 minutes to try this. Please try this. Okay, have you gone through the basics of the ring, basics of ring theory? Like, I mean the basics of ring theory. Like, if P is prime, then R mod P is an integral domain. If M is maximal, then R mod M is a field. Was integral domain defined here? Let me see. Integral domain is given in 116 page. Okay, where are we? Yes, so integral domain has been defined. Okay, so so let I mean R be simple. Take A belongs to R. So what we will have to do? We will have to show that this A has an inverse, right? Okay. So consider this ideal generated by A. Okay. Consider this. Do you know the meaning of this? This. Are you guys familiar with this notation? This is nothing but A times R for R belongs to R. Okay. This is an ideal generated by A. Now, since R is simple, is 0 or R, but A into 1 belongs to this, so not 0, this implies to R, right? So what do you get? 1 is there in R, right? This implies 1 belongs to A, right? So there exists B belongs to R such that A into B is 1. Okay. So this B is the unit. Okay. So A is invertible. And for the other part, let R be a field. Okay. If I is any ideal in R, take A belongs to I, since R is a field, A inverse belongs to R. which implies A1 that is equal to A inverse into A belongs to I, which means I equals to R, right? Because if one is in an ideal, then the whole ring, then every element of that ring is in that ideal. Okay. So this is done. If this is a ring, possibly without identity, no proper ideal. Let R be a ring with identity, and is the ring of n cross n matrices over R. Okay, M and R. J is an ideal of S. If and only if J is the ring of all n cross n matrices over I, where I is some ideal in R. Understand? So they are saying that every ideal J of M and R is of the form M in I, where I is an ideal in R. Okay. This is a very standard result. This is a very standard result. Okay. So I will send you the solution. Okay. Because this is nothing but calculation. So I don't think we should be wasting time here. I will send you the calculation. Someone here is Ognidipto Ishan. Ishan, please remind me of this, okay? Please remind me that I am supposed to give this solution of this particular problem, okay? Okay? I am not doing it because this is just calculation, okay? So I can just give you the solution. S is the ring of n cross n matrices over the division ring D. S has no proper ideals. Why there is so? Okay, so they say that this is a principal ideal ring. Do you know what is a principal ideal ring? Let's do this problem. Let's do this problem. A ring is called principal ideal ring if a ring R is called if every ideal in R is principally generated. That is, I is of this form. Okay, so I is generated by a single element for some A belongs to R. Okay, if R is an integral domain, then R is called PID or principal ideal domain. Okay, so you are told, I mean you are supposed to prove that Z is a PID. Okay, so I give you again 2 minutes. Please try this, that every ideal in Z should be of this form. Okay, please try this. So let I be an ideal in R. Okay, if I is 0, then we are done. So suppose I is non, which imply there exists R not equal to 0 belongs to I. Also minus 1 times R, which is minus R, that belongs to I, right? I mean we are talking about Z here, sorry. Our R is Z, huh? The set of integers. So at least one of R, at least one among R minus R are positive, which imply mod R belongs to I. Okay. Now define the set I plus such that set of all mod R such that R belongs to I. Okay. So basically you are picking up the elements in I and you are taking their mod and you are just putting them in this I plus. And as you can see, if R is in I, minus R is also in I. So R with and without the sign is in I, right? Both I mean positive and with both with positive and negative signs, R is in I. So this is clearly non-empty. I plus is a subset of natural number by well ordering property. I plus has a minimal element. Weight ordering property says that every non-empty subset of the natural number must have a least element. Say A. Okay. Claim I is generated by A. Take R belongs to I. Now see, we can divide, we have the division algorithm on Z, right? We have the division algorithm on Z. So R will be like A into Q plus some S, where 0 less than A less than, 0 less than S less than Q, right? Right? If S is 0, then R is equal to AQ, which belongs to I. Otherwise, if S is not equals to 0, then S equals to R minus AQ. Now see, this is in I and this is in I, which imply S is in I. S is in I. But S belongs to, S is in between this. Now S is not equals to 0. So S is in this, which implies S belongs to I plus. Zero less than S implies S belongs to I plus, and 0 less than S less than A contradicts the minimality of A in I plus. Okay, so S is 0. Thus I, every element of I is a multiple of A. Okay, here every homomorphic image of a principal ideal ring is also a principal ideal ring. So they are saying that, so B says, suppose phi is a map from R to S, phi is surjective. Okay, then if J subset of S, then R PIR principal ideal ring implies S is PIR. Okay. So just take any ideal, take I subset of S, be any ideal. Now if inverse I is an ideal in R. Since R is a PIR, if inverse I is generated by some A. Okay. Claim I is generated by FA. Okay. So let S belongs to I. So if inverse S belongs to I mean belongs to F inverse I, which is generated by A. So if inverse S is of the from some A into R for some R belongs to R, now S equals to FA times FR, which is in. Okay, so basically you have shown that any element is a multiple of FA, right? Which implies I equals to FA. Okay. Zm is a principal ideal ring for. So what is Zm? What is Zm? So Zm is what we call Z mod Mz, right? Which is the set of these classes. Modulo M, right? So clearly you can define a map from Z to Z mod Mz where you take an element and you send it to their class. Okay. So phi is a ring homomorphism. Now just use B to conclude. Okay. Then this is just a homomorphic image of Z. Okay, do this. Repairing with do 11. And try 13. Okay, so see, we have used something here. Okay, we have used something here. F inverse I is an ideal. We have used this. Okay, that is something which will be proven in 13. So try 11 and 13. You have 5 minutes. Okay, so let's try this. So I think number 11 is quite obvious because you are quotienting out by the set of all nilpotents. So the quotient ring should not have any nilpotents in it, right? And r to the power n is 0 plus n for some n belongs to natural. But what does it mean? It means r to the power n is in n, right? Since n is a radical ideal, this means since n is a radical ideal, we have n equals to root n. So this implies r belongs to n. So r is 0. The only nilpotent element is 0. Okay. So if inverse J is an ideal, that's fine. What is car F? So car F is all those R belongs to R such that if R is 0, right? So this is nothing but if inverse of that 0 ideal, right? So 0 ideal is a subset of J, which implies car F equals to F inverse 0 ideal, the subset of F inverse J. Okay. If F is an epimorphism, then Fi is an ideal of S. Epimorphism means F is surjective. So suppose if R to S surjective, then I ideal of R. Okay. So suppose R and S belongs to Fi. Okay. So there exists X, Y such that Fx equals to R and Fy equals to S because F is surjective. So X plus Y is in I, which imply Fx plus Y equals to Fx plus, I should be writing like this, which implies R plus S equals to f of x plus f of y, which is equals to f of x plus y belongs to Fi, right? And again, say R belongs to Fi and A belongs to S. There exists X belongs to I, Y belongs to R such that Fx is R and Fy is, Fy is A. So AR is basically if y into fx, which is if yx belongs to fi, as yx belongs to I. Okay, so this is an ideal. But what about the counter example? So take counter example, that if we remove the condition of surjectivity, then this result fails. So take if from Z to Q, which is an injective map, you are sending elements of Z just into elements of Q. Okay, just the injective map. Now Z has proper ideals, right? But Q is a field and hence simple. So if I is not an ideal, if I is never an ideal, if I is not 0. Okay. Okay, I will be teaching this example actually. Otherwise, there are some really good problems. Like P, like P is an ideal not necessarily counter neighboring, then the following conditions are equal. P is prime. No, this is not needed. Okay, so we will prove this version actually, that so how was a prime ideal defined here? Oops, Chinese remainder theorem was there, right? Ishan, are you here? Are you there?
Yes.
পরদিন আমাকে মনে করাবি, রিমাইন্ড মি that we are going to prove that I mean Chinese remainder theorem, okay? Because I
Okay.
don't know whether I mean all of you have done it or not, so it's better that I do it here. Oh, Oh, so it is given here, right? Prime ideas, they are given. Okay, so this is an excellent problem, and soon, I mean, probably in a commutative algebra course, you will see that this the collection of all zero divisors. This is basically union of some prime ideals, not all, union of some prime ideals. So how to prove it? Okay, so there is a way to do it. Uh, So observe that R minus, say R be the ring, let R be the ring and Z be the set of all zero divisors. Okay, R minus Z is multiplicatively closed. That is, if Rs belongs to R minus Z, then Rs belongs to R minus Z. Now that is obvious, na? Because if R is not a zero divisor, it is obvious. Because as if Rs are not zero divisors, Rs cannot be a zero divisor either, right? Okay. So if R is not in Z, S is not in Z, then R minus Z is also not in Z. Okay. Now take S. What is S? Set of all ideals in Z, in R, set of all ideals in R such that I is contained in Z. Okay. So all those ideals which are contained in Z, you form the collection. S is non-empty as 0 belongs to S. Okay. Now you can take a chain and show that that particular is in by Zorn's lemma. So you can take a chain and show that chain has an upper bound and so on. So by Zorn's lemma, S has a maximal element. P. Okay. We claim that P is prime. So let A, B be two ideals in R such that A be in P. Okay. If A, B, if neither of them are in P, then P plus A and P plus B strictly contains, these are two ideals that strictly contains P, right? And since P is the maximal element, neither P plus A and or nor P plus B, these are not contained in Z, okay? Because P was a maximal element of S. So P plus A, P plus B intersect R minus Z, right? So let P1 plus A belongs to P plus A intersection R minus Z. P2 plus B okay. Now, since r minus z is closed under multiplication, p1 plus a times p2 plus b are in r minus z, right? But you see that this is p1 p2 plus p1a plus p2b plus ab. You see, this is in a, this is in p, this is in p, this is in p, and this is in ab, right? Which is a subset of p. So this whole this element belongs to p, which is a contradiction, as p belongs to s implies p is a subset of z. Okay, so p is prime, because then either a minus either p plus a or p, I mean then either a or b is completely contained in p. Okay, okay, so we will conclude today's class here. Let's try the next exercises in the next class, but we will have to complete it by the next class, because then we will go to factorization of rings. Okay, that's it for today.